It's about time to move on to our last speaker, Antje Wulff. Are you able to share your screen?
Yeah, one moment. Okay, can you see my slides?
Mm-hmm.
Okay, great. So yeah, hello, welcome. My name is Antje Wulff, and I'm very happy to be able to present to you an open platform approach to enhance the multiple use of data. So first, a quick outline, and after introducing the topics of medical decision-making and the multiple use of data, I will go through the open platform approach and our Medical Data Integration Center, which both arose from the Medical Informatics Initiative, the core principles and architecture of such an approach, the clinical information modeling, as well as data integration and querying. And after that, I will present an exemplary use case for using existing clinical data and the open platform approach to design a clinical decision support system and also further AI applications in a real medical use case. I will end my presentation with a short conclusion on multiple use of data and data integration. Let's start. I would like to introduce my talk by speaking of medical decision-making, as this is one of the prominent reasons why we would like to reuse medical data at all. Because solving complex decision-making issues is a key aspect during medical research, practice, and routine care. However, medical experts mostly have the ability to solve even very complicated situations by relying on the traditional way of following evidence-based medicine, comprising scientific evidence delivered by RCTs, guidelines, or expert agreements together with feelings and experiences. However, this evidence might be lacking in some scenarios. Sometimes the right data needed is not available in a timely fashion or even distributed in different systems. And at the same time, clinicians are often challenged by a stressful working environment. Consequently, there definitely is a strong need for being supported in decision-making processes. One possibility of support might be the implementation of so-called clinical decision support systems, or AI applications, that are able to reuse routine data, bring them together, and analyze them to gain new insights or to make decisions. Fortunately, availability and accessibility of routine medical data is increasing, and with it the possibilities of reuse this existing data for other purposes than the initial clinical documentation. However, the development of methods and systems that enable such an effective utilization of medical data from different primary source systems is a great challenge. And that's why currently, big data produced in the healthcare system indeed may be valuable for gaining insights for care and research, but is currently not efficiently used. And this is where the Medical Informatics Initiative and our open platform approach comes to effect. The Medical Informatics Initiative strives for establishing a national infrastructure to enable the secondary use of data within and across hospitals, and it will lay the foundation to establish a learning healthcare system and also data-driven medicine. HIMED is the name of one of the funded consortia of this initiative, and it covers about a quarter of all German university hospitals. HIMED's goal is the establishment of an interoperable and open health data platform, which will enable the cross-institutional data access, analytics, and sharing to improve patient care and clinical research. The feasibility of the open health data platform will be demonstrated in 3 clinical-driven use cases. One from oncology, in which a cross-organizational molecular tumor board is established. Cardiology, in which data also from wearables are integrated to predict heart failure. And infection control, in which a smart infection control system able to support an outbreak detection in hospitals is designed. For example, for the latter, we are currently standardizing and integrating microbiology laboratory reports into the open platform. But why do we need an open and interoperable health data platform, and how hard can it be to build such a multiple use of data network for hospitals? To comprehend this challenge, we have to understand that each hospital typically comes with a specific, unique, and complex information system infrastructure, such as this one. And this is a real snippet of the application landscape of the Hannover Medical School in Germany. And as you can see, there are a lot of different applications that are either connected or aren't connected to each other. It is important to know that each of these applications has a specific database and data structure such as these. This is a real database structure of one of our primary source systems. And moreover, it is not the case that the same clinical parameters such as the blood pressure value are represented and structured in the same way across applications and definitely not across institutions. So, to be able to obtain data, to reuse data from these applications, you have to understand such databases from the slide, as well as all of these data items inside these tables. And of course, when you would like to use an exchange data and research network, you face this interoperability problem multiple times at each institution. The idea of the HINET consortium to solve this situation comprises the design of an open health data platform that facilitates the reuse of data and the development of applications. The core principles of the platform have been defined as open service models, meaning that all specifications of the interfaces are openly accessible, open system specifications, which defines that all components and also protocols are openly specified using licenses feasible for both commercial but also non-commercial use, and open information models, meaning that all clinical models used for representation of data are well defined based on established and open information modeling standards. All of these principles have been technically composed, resulting in an architecture consisting of different building blocks, such as different services, interfaces, and standards. So, for example, we define a master patient index, and all of these interfaces require to use PICS-PDQ from IHE, which is a service for patient identifier cross-referencing. Then we have FHIR, terminology services, which serves us with international codes such as line codes, ICD codes. We have things like provider registries and patient consent management using also IHE standards. And for the structured data, we agree to use a standard called OpenEHR. Of course, we also need some standards for security and privacy and management of the platform. And on the top of these interfaces, we are building different kinds of applications. We will not go into further details on these blocks, but it is important to know that this architecture is realized in every so-called medical data integration center, MEDIC, at each participating site. Furthermore, there are some overarching services that would allow to exchange data between these hospitals and medics. However, coming back to this, to exchange data and to assure that every medic is really speaking of the same thing, we defined the principles of having open information models. Therefore, semantic interoperability, but also semantic traceability and clinically led data modeling have been considered as the key principles to reach a harmonized and also consented data representation on our platform. To assure this kind of semantic interoperability, HINET adopts the OpenEHR approach for semantic modeling. And OpenEHR is an open standard specification that describes the management, storage, and exchange of healthcare data and electronic health records. It is based on the idea of having a tool-level modeling, separating technical from domain-specific content. And therefore, it comes with a reference model that specifies general things such as data types and data structures. And the clinical information itself, such as a heart rate value, then can be modeled as so-called archetypes by applying constraints on the reference model. OpenEHR is used in different international projects, which is why many internationally reviewed and agreed upon archetypes already exist, which of course should be reused rather than modeling new things if possible. This is an international model for heart rate, and it contains the data section with the heart rate itself, defined with a quantity data type, but also other fields such as the regularity of the heartbeat. And this field is coded with a predefined list of values, and it can be even linked with terminology. For HIMATE, we designed a clinical knowledge governance framework that supports the management and the modeling workflows and processes. The overall idea in the Medical Data Integration Center is that data in the primary source system is identified and extracted, transferred into a standardized OpenEHR format, such as these archetypes, and loaded to an OpenEHR data platform, from which then this harmonized data can be reused, for example, for AI applications. These applications or analytic scripts are then independent of the local data representation. And of course, also the semantic meaning of the data processed in these applications can be assured so that this application itself is interoperable. This is a more technical perspective of a Medical Data Integration Center. This is the care provision domain of our Hannover Medical School, MEDIC. On the left, you can see the care domain with all these primary source systems. And we are mostly using a communication server that is receiving HS7v2 messages from these primary source systems. And we are mapping the primary data structure to a standardized representation using this consented, open, and mostly international OpenEHR model. The data is then stored in this new format on a specific OpenEHR data repository, which comes with open APIs so that applications can be built up on top of this. Besides using a communication server or commercial integration platforms, for this data integration task, meaning the mapping of primary data to OpenEHR data models, there are also other tools or workflows possible. For example, sometimes we are also using self-developed tools built with or on Microsoft SQL Server integration services or Altova MapForce, or even system-specific interfaces to really map the original data to our consented models and load them. Data on this platform also can be accessed. It can be accessed by a specific query language called Archetype Query Language, AQL. Querying with AQL does not require knowledge on these specific databases I've shown, as it formulates queries directly on the OpenEHR model. And here you can see a query that retrieves the timestamp of a laboratory test result and the result value from a given electronic health record. And in the where clause, you can find out which results are queried. In this case, we are looking for all laboratory tests corresponding to a line code 7708. And this is the international line code for neutrophil counts in laboratory test results, which has been binded to the result during our data integration process. Furthermore, we are only looking for lab results from a specific time window, and we like to order the results. All of these happens on the level of the model and not the database structure. So AQL is technology neutral and semantically enriched, of course, but also vendor independent. This allows also the sharing of queries with other institutions because we are using the same semantic standard. And as you can see, the query only relies on the consented models. Consequently, also applications or analytics scripts using the OpenEHR API and our models and AQL can be shared. This leads us to an exemplary use case for reusing existing data and integrating the data into our standardized platform and also designing applications from the field of pediatric intensive care. One important example from the clinical routine in this intensive care setting is the diagnosis and the therapy of so-called systemic inflammatory response syndrome, SIRS. SIRS was first introduced in adult medicine to describe a non-specific systemic inflammatory process in the absence of an infection. It is manifested by the presence of at least 2 out of 4 criteria, for example, abnormal temperature or leukocyte count. In case of positive blood culture or suspected infection with response to antibiotic treatment, SIRS rather becomes sepsis. Rapid recognition of SIRS in the intensive care unit is of great importance for the clinical pathway of the patient, because when the clinician is able of rapidly recognizing SIRS at the very beginning, an early antibiotic symptomatic treatment can be instructed so that sepsis can be prevented. Sepsis itself carries a high risk of progressing to severe sepsis, septic shock, and organ dysfunctions and failure, which is the reason of very high mortality rates. And all of these then could be prevented. There's a great chance of having an early full recovery. In case of missing a SIRS episode within the patient or being late, there still is a chance of having a full recovery, but there's also the highly increased chance of having only a partial recovery or death. So the clinical problem is that SIRS detection is challenging, and of course, clinical decision support systems that rely on routine clinical data may have the potential to support this clinical task. However, currently CDSS for this context are either not available, not evaluated, or not adopted in routine, which also has something to do with the fact that semantic interoperability and also standardized data representation are rarely considered in current approaches. So consequently, the objective in our project was to design a CDSS for detecting SIRS in pediatric patients, but with consideration of semantic interoperability features and also our open platform approach. Therefore, we designed a knowledge-based approach based on international guidelines and expert knowledge. We reused existing routine data such as vital signs, laboratory values, and procedures from the primary source system of the pediatric intensive care unit. We integrated this data into an open EHR-based data platform, similar to the HIMID open EHR platform. We designed also prototypical implementation of the CDSS, and we evaluated it in a prospective clinical study. Here you can see the CDSS architecture. We modeled and reused standardized archetypes, open EHR archetypes for this, such as for respiration, for body temperature, pulse, and so on. We queried the data by using AQL as query language. We inserted it into our working memory of our CDSS, and of course here are the expert rules and international guideline rules implemented. Here you can see the prototypical graphical user interface. It shows one intensive care day of a patient, and in each row you can see the vital sign or laboratory value which are important for this. On the right, you can see the corresponding normative values for the patient's age, and the red blocks represent the pathogenic phases for this patient and for this parameter. On the top, then you can see each specific SIRS event or episode labeled and reasoned by our CDSS. These are the data items currently used in our CS project and available in a standardized form on our platform. The dataset comprise parameters on vital signs such as respiratory rate, heart rate, but also laboratory parameters such as leukocyte count, procedure and device associated values, such as mechanical ventilation or cooling devices, and of course patient data such as birth date. The data sets are mostly multivariate time series. Vital signs are usually measured per minute. However, sometimes there is asynchronous sampling, as body temperature is not always measured automatically, but manually, perhaps only twice a day. Currently, there are about 2,000 intensive care days of 168 patients integrated into our open data platform. And these patients come with about 3 million heart rate and respiratory rate values and 1.5 body temperature values and some thousand laboratory values. Currently, we are integrating a lot more data into our platform. We have data available from the primary source system of the pediatric intensive care unit that comprise the last 5 years. And these are about 3,800 patients with 5,000 encounters. And these enhanced data sets comprise about 30 million vital sign values per parameter and 1.5 million laboratory values. Also, new parameters are currently integrated, such as standardized medication data, scores, or other device-associated data. Of course, also unstructured data is very interesting, such as the medical histories of the patients. For this, we implemented a prototypical natural language processing pipeline that is able to extract highly relevant information pieces out of an unstructured medical history of the pediatric intensive care unit, and it transforms it into a standardized open EHR template representation. Furthermore, we have data available not only from the primary source system of the pediatric intensive care unit, but also from other systems. For example, coded diagnoses and procedures are available from our hospital information system called ISH MED. And in our data platform, we will bring them all together and in a standardized form. And these enhanced data sets are already have been extracted from the primary source systems, and we are now ready to integrate it into our open EHR data platform. With these enhanced data sets, we would like to adapt and optimize our approach towards the detection and prediction of organ dysfunctions and failure. And now it is more about integrating data-driven analysis to find relevant patterns for patients with similar critical courses of disease. In the long term, we also would like to be able to support medical decision-making in intensive care by predicting which patient needs immediate attention, because the critical phase will occur within the next few hours. Some of these questions are covered in one of our funded projects called ELISE, but there are still a lot more things we would like to discover from these valuable data sets. Altogether, not only intensive care, but many medical domains can benefit from applications that are able to reuse and analyze data to assist in medical decision-making. However, a strong focus on bringing data from different primary source systems together and also considering semantic interoperability standards in your data integration process is needed to really efficiently reuse and share data as well as applications. And as presented in the end, the establishment of such an open data platform enables us to design and implement valuable interoperable AI applications and clinical decision support systems. And thank you.
Thank you for a good talk. Any questions from the audience? Okay, I can see a hand up from Marika. Was it? Yep.
Antje, could you unshare your screen?
Yeah, of course.
Marika, you should be able to unmute yourself now.
Marika, can you unmute your mic? I'm not sure what's happening there. There was a second hand up at one stage. Perhaps we go with the second question. Sonam Kumar.
Yeah, hi, thanks for the great talk. There's some issue with my video, so yes. So my question is about the ethical issues that might be that we might face while creating the database like that. So what are the issues that you have faced, like did the patients protest against their data being or something like that?
Your voice was quite broken up. I don't think, and looking at the faces of other people, I don't think anybody could really construct your question. Can you try again?
Yeah, is it better now?
Yeah.
It's better now, I guess. It's so?
Yep.
Okay, so my query is whether the patients from whom the data was being taken had any questions regarding the integrity of the data, the privacy of their data. Like what are the challenges that you had faced while taking the data from them? So you see, the cohort size was around 4,000 patients. Now, if we want to make a database of a bigger number of patients, so that we can get a variety of data, qualitatively the data will be quite rich. So we need to increase the cohort size, probably by a scale of 10 or 100. So what are the challenges that you faced while having this study? That's the question I have.
Okay, thank you. Yeah, the privacy issues, are really big issues, and in the HIMID consortia and also in the Medical Informatics Initiative, from which all of these use cases arise, we have had a lot of discussions on data security, on data privacy, and we've come up with some solutions for that. But I have to admit, this is a completely different work package, and we have some laws that allows us to reuse data that come from past years. So these are historical databases and historical data. And of course, we can't ask all of these patients now whether they consent. But of course, this data in our research domain is pseudonymized. So we don't have clear names, and we don't have any addresses or something like this. However, in some cases, we need some things like birth date, especially in pediatric settings. Birth date is very important, and therefore we had to tackle many challenges and many talks with data security experts. And however, for our data set from the pediatric intensive care, these 5,000 patients, all of these data security issues have been solved, and we are really allowed to use this data. We have talked with a lot of data security officers for this, and yeah.
And maybe adding to that, this already, probably Antje, correct me, this is the biggest database in Germany, considering pediatric ICU data. So it's not easy to just enhance this by a factor of 10 or 100 or so, yeah?
Yeah, that's correct.
Marika Prine, if I pronounce that correctly, are you still intending asking a question? Okay, I don't know what that means. I can see from the attendees, someone's got a hand up, but the name is all in Chinese characters, which I can't pronounce or read. But if you can hear me, can you ask your question?
Hello?
Hello?
Yeah, yes, thank you so much. And thank you so much for the talk. And I would like, I'm Amber, and I'm from Taiwan. I'm a master's student studying biomedical informatics. So like the previous attendee also asked about the privacy, and I'm also aware that there is a system, and it's called Common Data Model. So it's also shared. It's also used to share medical data between different institutions. So what you have introduced in your presentation, I guess that it's not a common data model, and I would like to ask what is the difference between these two, and what are the pros and cons? Thank you.
Okay, yeah, so I think your question refers to our standard. We are using OpenEHR. Of course, there are other standards for clinical information modeling and representation. As we heard in some of the talks before, there is FHIR that also can be used to represent data in a consented format. We have the OMOP model you mentioned. However, we decided to go with OpenEHR for some reasons, and I think this has also something to do with some other issues like political things, whether tools are available, any industry standards. However, we decided to use OpenEHR for representing models, and this decision also has something to do with the fact that many international projects now evolve using OpenEHR. And we visited some of these countries using OpenEHR in their national standardization projects, such as from Norway. And they had very good experience with using OpenEHR. And now, after 3-4 years of our project, I think we can say that it worked. It works, and we rely on the standard. However, you're right, there are any other standards, and we are now also trying to bridge standards. So for example, we're also trying to bridge FHIR models to OpenEHR models. And of course, there are other standards that maybe also can be bridged.
And if I may add again, sorry, Antje, the common data model, the OMOP model, is a very simple model that is not fit for building clinical decision support systems on top. It's just a very simple model to gain huge amounts of data.
Yeah, and we also, I think we also heard about model of use and model of meaning. And that's why we also decided to go with OpenEHR, because OpenEHR can bind terminologies to our OpenEHR clinical model. And this is very valuable because in some, you need terminologies and additional codings to really have the full picture. And I think that other standards also might be possible in future to do this, but OpenEHR really can capture these things.
I can see a question from Shanila Basir.
Yeah, thank you so much for the nice presentation. I'm also working on the knowledge graph creation for the immune system, and I'm a student in AMHA, but we are working with the employees of the health employees of the MHA, their data, but we are not allowed to store the data even on our PCs, even on any of, because it's it's with just IDs, fake IDs, no real name, nothing. But you know the protocol of MHA is very strict regarding these stuff. So. And also there is a separate server that we ordered only just to store this whole data and the knowledge graph and all these things. So how you are tackling, because you are handling, and even we have only 25 donors and you are handling 4,000 patients data, how you are tackling with MHA authorities then?
Perhaps we need to talk to each other apart from this presentation. But yes, I can agree. It's very difficult, and we had a lot of talks. But in the end, our medic approach got approved by the data security officer. I don't know. Perhaps you talked to another data security officer. I don't know. Perhaps we can talk about this after the talk, because I think it's some internal stuff. But yeah, our approach got approved. Yes.
Yeah. Okay. Thank you so much. Then.
Okay. There appears to be no further questions. So thank you to all the speakers. Wolfgang, do you want to say anything before the session ends? You're muted. You're muted.
Thank you. I guess I'm just looking forward to the last session, and I'm hoping that the last session will be as nice as this one. So I enjoyed it a lot, and I hope to see all of you at 3 o'clock again for the fourth and last session.
10 minutes later.
Okay. We start 3:10, right?
Yeah.
Perfect. Okay. Looking forward to see all of you at 3:10.
Bye.
Bye.